All right, well, it looks like people are starting to come on in. We'll wait a few more minutes for people to keep on joining, but we already have looks like 22 people coming in already, so that's awesome. Jake, your slide is still up. If you want to leave it up, that's fine. But welcome on in, everyone. We'll start in just a couple of minutes. Okay, well, maybe we can get started, and we can just kind of start the introduction now. It's like the previews before a movie. It takes 10 or 20 minutes anyway for people to show up. 10 minutes late. So my name is Jack Gillespie. I'm the Planetarium Manager at Grand Rapids Public Museum, and we have a great guest speaker today that we brought to you with a partnership with the Grand Rapids Amateur Astronomical Society, Astronomical Association. And looks like we have a great crowd. We already have like 25 people hop on already. I see some of my museum friends are on there, and it looks like we have some GRAAA people, and hopefully we have some new people though, some new people that saw our posts on Facebook that just wanted to check something new out. And so we have with us Jacob Bourjaily, but we also have Chris Miller, who's the president of the GRAAA. And if you want to take it away, Chris.
Okay, welcome everyone to this evening's virtual event. In fact, these events this platform has offered us an ability to reach out and to, bring some people into our circle who we would normally not be able to have in a presentation. As part of the Grand Rapids Amateur Astronomical Association, I wanted to welcome everyone and say that, we have been working this year. We've actually had, this year, if any of you have been following us on grAAA.org, we have had a number of public events, that is evenings where people can come out, view the stars. Actually, I have an image behind me here that actually I took this summer. It's the Heart Nebula out at the Wien this summer. It was a good summer for doing some imaging. And this evening, we're going to be, of course, moving into a different topic, but I also wanted to mention that at the observatory, we continue to move forward. Aside from having, a limited public schedule this year, we also, the image you have in front of you, at least I assume, Jack, that they all have the image in front of them of the lecture. That is the observatory building itself. The dome that is on the left this summer, or just this fall, we successfully had it retrofitted. It's actually a 50-year-old dome, but we had the mechanical components rebuilt by the original manufacturer this summer, and it is now back to perhaps ready to serve another 50 years. We will see. Also, we have recently just been successful at an application for a grant from the Lowell Look Foundation. And yeah, it's not an exciting kind of grant. We're going to be replacing, again, a 50-year-old water well. But in doing that, we are going to, it's kind of laying, if you will, the foundation for the future. It will give us a more reliable water supply and allow us to expand the building should we, we're hoping to do that some point in the future. Anyway, so I will move on to, so with that, just a little introduction, just a little plug for the GRAAA, and be sure to look at, we're kind of closing out the 2020 season, but in January, we're going to be cranking up the 2021 season. And we've got some good programs that are being organized by our program manager and former president, David DeBryan, also former director of the Planetarium. And I will turn it over to him to talk about some upcoming events and to introduce our speaker.
Thanks, Chris. All those formers make me sound rather ancient. And yet I really, really do appreciate still being engaged with the association in a sort of relevant capacity. And that includes arranging for some pretty intriguing programs, beginning with the one tonight. Having one of our most distinguished alumni back is always a pleasure. And I'm happy to say that I keep in contact with Jake. We're still very close friends, and we do keep up with each other's lives on a pretty regular basis. Next year, we will be meeting virtually all the way through at least March and quite possibly beyond. And we have 3 programs set up already in that period. One is Dr. Brent Boss, who is a planetary specialist and also, like Jake, a native of this area, who went on to do work at the University of, I believe, at NASA and also at the University of Arizona. And he was very much involved, Jack, you might be interested in knowing this. He's involved with the asteroid mission. And I think you've already met him, if I remember correctly. And he'll be with us on, I think, January 20th. We have another wonderful alumni called Zach Berta Thompson, I believe is he now goes by, and a young man that grew up in Rockford who's a leading expert on exoplanets. And we're expecting to have him speak to us at some point in the spring, along with Mike Sinclair, who is a stalwart in the Kalamazoo Astronomy Club and has a wonderful program on the famous Curtis Shapley debate. These 2 famous astronomers with fairly big egos discussed their concept of the Milky Way galaxy back in the, I think, 1920s, when we were just starting to try to understand the structure of our system. And so that's what's coming up in the spring. And then also our rescheduled 50th anniversary, I guess we call it 50+1 of the Wien Observatory, which we absolutely want to happen this year, which will be on the 26th of June. And hopefully we'll be back to some semblance of normality by then, if everything works out. So there's a little bit of what's coming up. We had a really successful public night season, even though we didn't start it till July 29th. And I believe close to 1,000 visitors over the course of about 5 nights that we were able to conduct toward the end of the season. Tonight's program, as you can see on the screen, is a memorial to James M. Marron, who actually came to the Grand Rapids Amateur Astronomical Association, I believe, around 1962 or 3. He had only been married a fairly short time, had 2 young children, and I happened to meet him, I myself being fairly young at the time, at a gathering of the amateur group at a place called Bird Hill, which is in an area of Grand Rapids that was dark at the time, but is right about where Celebration Cinema is today. And because of the growing urban sprawl, the association was trying to find someplace better to do their observing. And it was also about that time that the words of James C. Veen were echoing. He was the founder or co-founder of the group and had envisioned an observatory. And as it was discussed more and more, Jim Marin, who was on the board of the GRAAA at the time, and I was also on the board then, having come to Grand Rapids in '64 to participate in the development of the planetarium, And we were stymied. We were really, really stymied because the cost of getting land for our observatory would be prohibitive. And it was about then that Jim and Evelyn, his wife, made this decision to let us build it on their property. And for decades after that, they were just such wonderful landlords. But at the same time, I can't help but think in the back of their mind, they were sort of regretting that decision, because we were an intrusion, but they were unfailingly courteous, cooperative, helpful, and very much in control of their emotions. So without the Marin family, we would not have the Wien Observatory. I'm fully convinced of that. And Jim was a stalwart throughout many, many, many years of operation of the observatory. He was a regular presenter at the club meetings. He really, really had a great passion for cosmology and deep thinking. He was actually a social worker for the, I think, Michigan Department of Social Services. And yet, he was just an ardent astronomer, also an actor. We utilized his voice for narrations at the Planetarium, and he also worked there part-time during the 60s and early 70s. And was just a remarkably thoughtful, compassionate, and very, very social person, somebody that we all treasured. And we lost Jim almost 3 years ago now. And after that, we decided that one of our events each year, one of our programs each year would be named after him, the Jim Marron Memorial Lecture. I think Jake will probably have a few things to say about Jim too, because he's old enough to have remembered him personally. So let's talk about Jake a little bit. And I'm not going to tell you everything because there's so much to tell. But I think you could sum it up by saying that this young man has been a standout since he joined the GRAAA as an 8th grader back in the late 1990s. He was soon the junior representative on the board of directors, interacting with adult members of the board in a very adult way. At the time, he was also simultaneously working on requirements for an Eagle Scout and proposed to the group as a community project the installation of confidence lights that are still lit all along the drive to the observatory on public nights. So Jake, we think of you every time we have a public night. And I think of you each time when I have to service those lights every spring. But they've been a great asset. While in high school, he also became an intern presenter of sky shows at the Chaffee Planetarium, and then a part-time producer of programming, specializing in light shows. In fact, Jack, I think you'll see his credit up there for the current light show, Dark Side the Light Show. Jake he just came back to do that as a courtesy to us and for relaxation. That's what Jake does for relaxation, because most of the time he's got his head buried in theoretical physics. He graduated from Forest Hills Central High School in 2002, becoming recipient of the prestigious Roger B. Chaffee Scholarship, and then going on to complete graduation requirements at the University of Michigan in just a couple of years. Then it was on to Cambridge University in England during the period 2004 to 2006 as a Marshall Scholar. Returning to the US, Jake studied for his PhD in physics at Princeton while simultaneously collaborating with other young scientists worldwide, and some of the older scientists too, because he was had an office and interacted with them at the Institute for Advanced Studies at Princeton. After getting the PhD in 2011, Jake moved on to the Harvard as a junior fellow in the Society of Fellows for 3 years. And after the Harvard experience, where he was able to again collaborate with leading scientists there and elsewhere, Jake became a researcher at the famous Niels Bohr Institute in Copenhagen, Denmark, where he remained for several years. Then in 2019, Jake decided to return to the US and to set down more permanent roots. But at the same time, he remained kind of in a joint appointment at Niels Bohr, while also accepting a new primary position, this time as associate professor of physics at Penn State University. He assumed his position very early this year, and of course that coincided with the COVID outbreak, so it's been a pretty interesting year for Jake. As he's tried to keep up his research, initiate some teaching, and all of the collaboration he's been doing. Luckily, he was used to doing it online, but he was doing it even more so now in the last year or so. So he's continued to engage and inspire budding scientists, as well as pursue research interests, which he's going to tell us all about. Jake does not have a lot of time for diversions, as you can guess, but one really significant one is the charming Tasha, an administrator at Penn State whom he married, and their daughter, Allie Mae. He's engaged in skydiving, playing the piano, reading Shakespeare, and other adventurous activities. He recently got a pilot's license, and I think you might have even planned to fly up here tonight, Jake, but COVID forced the cancellation of the in-person presentation. So here we are on Zoom. So welcome to all of you who are Zooming in. And it is my very great pleasure to introduce my dear friend and someone of whom I'm incredibly proud, Jake Bourjaily. Dr. Jake Bourjaily. I will show respect. Jake?
Thank you, Dave, for that very generous introduction. And thank you, everyone, for being available tonight and attending. I see a lot of really wonderful friends in the participant list, and I wish I could be with you today and to catch up and to share stories. I'll do my best with what we can over Zoom. So my talk today is necessarily, I gave a somewhat vague title because I wanted to give myself a lot of room for interpretation. And the story I'm going to tell today is a personal story. So it'll cover some of those details that Dave mentioned, and my path, my sometimes stumbling and often lucky path, going from an amateur astronomer to a professor of physics today. And I want to intersperse to the story will be some examples about what I work on and what I think is the most exciting thing going on today in theoretical physics, quantum field theory. And I know that that might sound a little intimidating, but I promise it'll be easy enough, or at least I hope I can convey the excitement that's going on right now in the field. So I want to start at the very beginning with the James C. Bean Observatory, a place that I think everybody in this audience has been to, including Tasha. I got my start in science and my love of astronomy and science and more broadly at the Hill, like a lot of us have. And I spent a lot of time, sometimes before class in the morning, would drive up, not because I liked mornings, but because it was a good way to be a human being by the time school started. Spent a lot of time on the telescopes, and to this day, whenever I go back, I drive up if it's a clear night and take a look at through the Hawkins telescope, still my favorite telescope in the world. And it's a real privilege. And I don't need to tell you here how nice it is to be looking at the stars and appreciate the beauty of the sky above and our ability to understand this. But one of the really great things about the Astronomy Association, in addition to the astronomy, are all the interesting people and great interesting people you meet and who become really great friends. Like many of you, and including many of you, I count some of my closest friends among the Astronomy Association. Some that I met, very dark at night and that only saw their faces later on. And important among, incredibly important among this was Jim and Evie. And the last time I spoke for the Astronomy Association, I think was in 2017, a few years ago. And it was a privilege to spend time with Jim and Evie again. And it's a great loss, but and I'm incredibly honored to be giving a talk in his memory. And of course, in addition to these, there are some very colorful people that you can encounter on the Hill. And some of the, my start in science in many ways starts on the Hill. And Dave, who you've met, and I'm sure everyone here knows, had a big influence on my life. In addition to training me on the telescopes when I was young, he gave me the opportunity to work at the Planetarium and get some practice talking and sharing my enthusiasm for science with the public, which is something that's been very important to me ever since. And I don't need to tell this audience about how important the Chaffee Planetarium has been. But I think I have to attribute my start in physics really to high school, and maybe not in the class you were expecting, but in Mr. Von Eyre's AP chemistry course. And I still maintain that chemistry is close, especially AP chemistry is closer in spirit to what a physicist does today than maybe an AP physics course, which I never took. Because in chemistry, you learn about atoms and electrons and neutrons and protons, and you learn about the periodic table and a lot of the structure. I'm teaching quantum mechanics now at Penn State, and we've gone through the hydrogen atom, and we're going to get to the periodic table right after the Thanksgiving break. And I've been excited about it, for weeks. And this was really my first exposure to physics. But even in a much more direct way, I remember Mr. Von Eyre pulling me aside once when I was young, telling me that if you are good at math and like science a lot, then you should probably look into physics. And I was skeptical at the time. I didn't know anything about physics, but it sounded a little boring maybe. But he pointed me towards the Feynman lectures, which had a profound influence on me. And long before I ever took a course on physics, I read through these. I listened to them on tape, borrowing my brother's audio player when I was driving around Grand Rapids, and came to college with a 1960s understanding of modern physics, saying some very strange things to my professors, I'm sure. And when I started at the University of Michigan, I chose the most sciencey part of engineering I could, which I thought at the time was nuclear engineering. So when I finished high school, I started as a nuclear engineering student at the University of Michigan. But I got my first exposure to real physics in Professor McKay's Introductory Physics 101, basic introductory physics. And I spent more and more time at the physics department when I was, a freshman. And one day when I was wandering around the halls, I saw a poster that caught my eye for a research opportunity at CERN. And to be honest, I didn't really know much about CERN. I certainly didn't know much about what was going on there, why it was important. But I liked the idea of spending a summer in Geneva, Switzerland, and getting paid to do it. That sounded really cool. So I applied. And I have no idea why to this day, because I didn't know at the time that this was nationally competitive, and I also didn't know at the time that it was almost always seniors. But for some strange reason, the people who organized this program, two very influential people in my life, Professors Homer Neal and Gene Krish. Homer Neal, who passed away a few years ago, and Gene Krish, I was in contact with just this week even. for some reason, they chose to give a nuclear engineering student an opportunity. And my life has never really been the same ever since. So at the end of after 1 year, just out of high school, I found myself at CERN in Geneva. And this was before the Higgs boson and a lot of the news. To give you an idea of what it's like, I have this short video that I hope transmits well over the over Zoom. So here we have the globe. Switzerland is over there by France, northwest of Italy. And there's that big lake there called Lake Geneva, naturally enough. And the collider is this giant tunnel, 27 kilometers, around 17 miles in circumference. And it's actually a series of older colliders that are all glued together to increase the energy of the particles. And the idea then, because it was really just an idea, the machine didn't exist yet, was that they would be colliding particles at very close to the speed of light. And in these giant, very tall detectors, they would measure the junk that gets created, this spray of stuff that came out of it. And from that, they could infer the laws of how the universe works, what the universe looked like a few millionths of a second after the Big Bang, and maybe discover new particles. That was the hope in 2003 when I went there. So a picture of it, just give you a better scale here. This is not, you can't see it from the sky, but this is the drawing of it over the environs. There's a mountain range to the left, and the CERN campus is on the bottom corner, and it looks like an arrowhead. And it just, in fact, actually it digs into the French-Swiss border. So by the time you're on the other side, you're in France. And there are 4 places underground where they have these big giant detectors where they were going to build them. I had an office right in the bottom right-hand corner of campus there in building number 45, which was, I felt very special as a young student. And this was the view from inside of it. It's the only pretty looking building at all of CERN. It's a very pragmatic place. And I even got to look underneath into the tunnel, but again, there wasn't a detector yet. I realized I don't have a picture of the actual detector. Imagine this whole 7-story cathedral underground is now completely chock-a-block full of modern electronics, very, very high-tech electronics that would, go in over the following years. But I got an opportunity to explore research, to learn a little bit about what they were doing, and to meet a lot of very fantastic people, many of whom are still doing science today, and many of whom I count as my colleagues. It was a really great group, and it's one of the really great things about theoretical physics, but academia more generally, is that you're surrounded by people who are really passionate about what they're doing. And you wake up in the morning and you do exactly what you want. And I was still a student at the time, and I was still learning a lot. It was like learning everything I possibly could about the standard model of particle physics, which is our current picture of how the universe works, and all the rules of the game to play it. Now, I'm not going to explain the standard model for you, but suffice it to say that the standard model of particle physics is essentially just a list. It's a list of particles and how they interact with each other. Because if you know those two things, you can predict the future. Although, of course, in quantum mechanics, the future is probabilistic, which means the best you can ever do is to make a prediction for how likely different outcomes are to happen. This is the modern version of force equals mass times acceleration. It's completely deterministic. It's just probabilistic are the predictions that we make. And how we get from this list of particles to predictions for experiment requires a bit of work and usually involve a textbook. And the textbook that I started with was this one. It's now been, well, it's still pretty much the standard textbook in the world. Quantum field theory is how you do it. And even though I'd never had quantum mechanics, let alone quantum field theory, I decided I would teach myself quantum field theory. And so in the fall, when I returned for my sophomore year, I enrolled in against the advice of all my counselors, in a quantum field theory course. And I've never looked back since. I've been doing this now for my entire career. So I want to give you, throughout this talk, I'm going to give you a bit of quantum field theory and how this game is played. And so what I want you to think of quantum field theory as, it's not a theory, it's not a theory, it's a theoretical framework. It's really more similar to force equals mass times acceleration. If you tell me the forces and you tell me the masses, I can predict the future. And just like that in quantum field theory, if you tell me the particles, actually you don't have to tell me anything else, and I guess the masses, then you can predict the probabilities of the outcomes of any experiment. And the relative probabilities of the possible outcomes for an experiment is encoded in a function called the scattering amplitude. And it's a function of many, many variables, and they're very complicated, and they're often very scary. Well, we'll come back to that. But the way that we understand quantum field theory, and the way that we still teach our students today, and I'm going to teach you, I'll give you an idea of how to play this game, is extremely simple. The probability for something to happen is simply a sum. You just imagine all of the possible ways that something could have happened. And there's a lot inside that little statement, but let me unpack it a little bit. And this picture of quantum field theory goes back to Feynman, who wrote those lectures I read as a high school student. The new idea of force is not a field or some, there's no analog of GMM, the divided by the distance between two masses squared for gravity, because particles don't have positions. Instead, what you have to do is imagine something happening. And the way it works is you draw a little diagram. I promise this is all very, very simple. So imagine you want to calculate the probability that two electrons bounce off each other. Well, you start off with two electrons. You draw dots and you just evolve time forward. And you imagine all the ways that they could go from the beginning, from the initial time to the final time. And the most likely thing to happen is that they don't do anything. They just kind of stay put. That is always the most likely thing, and it's always the most important prediction. But a little less important, but the leading next thing that could happen is that they could exchange a particle called a photon. And yes, those are the particles of light that we see with our eyes when we look through a telescope, the photon. And that's actually it. The rules for how we understand electricity and magnetism are as simple as that. There are two kinds of particles, electrons, well, there's also protons and a few other things. But if you just want to talk about how atoms work, there are particles that have charge, protons, electrons, and they can emit a photon and they can absorb a photon. That is it. If you know that one little thing, you can predict any outcome. Now, to actually go from a picture like this into a number for an experiment requires a ton of math and years of graduate school, and I'm not going to teach you that, and I'm not sure if it adds anything to the understanding. The understanding is as simple as that. Draw every picture you can think of that has that kind of a process in it. I'll give you an example of this that we usually give our students in quantum field theory class. So one thing that's important here is that a sum over all possible ways that something could happen is infinite. There's a lot of ways something could happen. And we're in good luck because every theory in the standard model, at least at high energies, and certainly electricity, has this property that the more complicated the picture, the less it matters. And so you start making a prediction with the simple pictures. And then the more complicated the picture is, the less it matters for the prediction. So you lead with the simple diagrams, and then you just keep going and adding more and more complicated things. And so, for example, this process of having this is not really an amplitude. It's if there are any experts in the audience, it's a ratio called the gyromagnetic ratio of the electron. And you start by just drawing all the diagrams. So the simplest diagram you can think of is just that. An electron emits a photon. Great. That, when you learn how this diagram converts into a prediction, tells you that the theoretical prediction for this ratio process happens to be the number 2. This won Dirac his Nobel Prize in 1933, believe it or not. Well, but the rule is we have to sum over all the ways it could happen. And is there anything else we can imagine happening? Well, that might happen. And it turns out it's the only one at this order. So it's just one little picture. And this picture turns out to be a very complicated function that we usually ask our students to calculate. It turns into about 2 or 3 pages of algebra. If you're a really efficient professor, you can get it down the blackboard in one lecture, in 1 hour. I mean, many blackboards, but you can do this calculation. And then you get this integral you have to do, and what is that integral? And your computer doesn't know how to do it. You have to learn some tricks. And anyway, after all the dust settles, and you're finally done, the prediction is, takes about a week of algebra. It's a homework assignment in every class. You get the number 1 times this factor, which always is there. So you do this huge amount of laborious effort to find the number 1. And I think more physicists should be more embarrassed about this. But that number 1 did get Feynman, Schwinger, and Tominaga their Nobel Prize when they calculated independently. And Schwinger was so proud of it that he put it on his tombstone. He divided it by 2 because he divided it by 2. Anyway, the next step, and I'm reviewing this because it's both representative and it's also typical. So the next one, you just have to draw all of the other diagrams I could imagine, and you order them by how many vertices they have. And the next set, there are only 7 diagrams, and I'll leave that as an exercise for you to draw. Honestly, you can draw all these pictures. They're not that hard. I think a precocious middle schooler could easily draw all 7 diagrams and the next 87 and et cetera. The diagrams are not that hard to enumerate. But if this one little picture took a week of algebra, this one, well, unfortunately, it takes about 10 years of work. And that was done first done in 1957. And the answer, okay, some number. Okay. The next one, to go any further than that, required computers. And in fact, it wouldn't be done until the 90s. So about 30 years of work to go higher orders. Completed in 1990, and now we know 1 order past that as well. And as you go, you get a better and a more and more precise prediction for the experiment. At the end of the day, you get this theoretical prediction that this particular number, when you measure it in the experiment, should be 2.002319 ... And you can ask your experimentalist friends to measure it, and it matches. In fact, this is the most precisely tested idea in all of science. There isn't any other corner of science anywhere, astronomy, chemistry, biology, nothing, where anybody has measured anything to one part in 10 to the minus 13. It's an incredible triumph. And it's also an indication that this general picture, this silly idea that you just add up all the ways that something could happen is right. It correctly describes nature. And it's a triumph of science, of modern science. And the basic rules of this game haven't changed at all since, well, there are a couple ingredients that were kind of important in the 70s. But more or less, we've been teaching our students how to play this game and how to do this week of algebra or 10 years of algebra the same way since the 1950s. And as I'll show you later on, there's quite a bit of excitement going back to these calculations. And I want to share with you why. But getting back to my own story, when I got back from CERN, I learned quantum field theory. And quantum field theory is usually the prerequisite to do research with a theoretical physicist. And it's something that very few undergraduates have to do research. And I was working with Homer Neal on, we had more projects. I went back to CERN another summer. And I also met this Professor Gordy Kane, who told me when I met him that he had never had an undergraduate student. He didn't, but okay, he would let me. And when he was told that he couldn't give me a graduate student office because I wasn't a graduate student, he gave me a professor's office instead. So I was quite a bit spoiled by the at Michigan there. And with him, I started doing research. I'm not sure if the slides are showing here, but we started working on dark matter, and I had my first dip my toe into communicating science and doing, an important part of doing science is writing your research up and also giving talks and sharing it with other scientists. And so I found the title slide for my first lecture, my first genuine seminar. I was invited to the University of Chicago and to the Kavli Institute for Cosmological Physics in February of 2005, before I'd graduated. And I'm actually pretty sure they didn't know that they were inviting an undergrad, which I'm very proud of still to this day. I gave more talk. This is my first talk at the GRAAA, was around the same time, in May of 2005. And so in 2005, in my third year of undergrad, I was at the University of Michigan when I was walking through a hall and I stumbled upon another poster that caught my eye. And this one was for a scholarship that seemed pretty impossible. So no loss, no harm in trying, called the Marshall Scholarship. And I didn't know much about it, but I applied, and for some accidental reason, I got it. And then I needed to figure out how to graduate. So I wasn't planning to graduate early at all, but this scholarship, I had to go. So I got my diploma. I met the British ambassador, and the Marshall Scholarship was funded to thank America for the Marshall Plan. So it comes from British Parliament and has all sorts of interesting, weird strings attached. But the output of this is that you get to basically pick anywhere you'd like to go in the UK, and you can go there for graduate school. So I chose Cambridge, but I knew I was destined to, I knew the right decision would be to come back to America for my PhD to do physics. And so while I knew I had a pretty good application package, I applied and deferred admission to Princeton. So I was planning to come back. Cambridge is probably the last time I considered myself a real student. I want to give you an idea of what Cambridge like, just because my brother, who's in the audience here, knows that when we first visited Cambridge, somehow we managed to not see anything and not even know that we missed it. But this is what this old illustrious institution looks like. And I lived on the right-hand side of this picture. And this is where I ate dinner every day. And I worked in this library there, the Wren Library. It's a very intimidating, beautiful place. When you enroll, they have you sign this book, this registration book, and they have on the table the same book that Isaac Newton signed when he became a student there so long ago. But the most of my time was spent in the math department, which was actually a pretty modern and quite a castle to mathematics. It was quite nice. Yeah. And I still managed to get outside and look at the sky every once in a while, see the aurora. This is a picture just above the Arctic Circle in Norway, on probably the only trip I took that year. But I studied, I took classes, and that was about the last time I ever did that. Because when I got back to Princeton, it was more or less the way it's been ever since, research. So turns out that I didn't know this really at the time, but Princeton also looks a lot like Cambridge, for good reason. They sent their architects over there to look at it and copy their archways and things. So this is where I lived. This was my house. The door on the left was my door. And when you looked inside, you saw that was my dorm room for 5 years while I was there. And I worked in really nice, it was a really nice place. And for the first several years I was at Princeton, or a couple of years I was at Princeton, I continued doing research, not related to dark matter, but related to particle physics like the Standard Model and extensions thereof. And this was something I did mostly by myself, with a few colleagues here and there, but it was really kind of my own thing. And I wrote papers, I gave talks. This was probably the last talk I gave on this subject at string phenomenology in Warsaw. It's one of those perks of science that I had no idea of before I was very much involved in it, that you really get to see the whole world. And it's for the simple reason that when there are very few people in the world who know what you're doing, who can understand you, you go out and find each other. And this is quite an interesting perk and quite a valuable perk, physics. So the next big change in my life, and really what set me on the course until today, was the appearance of this gentleman right here, named Nima Arkani Ahmed. Now, I knew about Nima beforehand, but earlier, and in fact, I'd kind of chosen to Princeton to avoid him. But it turns out that around the time, right after I had moved to Princeton, he quit Harvard and took up a job at that illustrious institution that David mentioned, the Institute for Advanced Study, which actually has no affiliation with Princeton, it's just in the same city. It's where Einstein had his office. It's this beautiful building, about a half-hour walk from campus, and this is what Nima's office looked like. And what struck me very quickly is that he was very, very smart. And although he was by this time in his career already very famous, he was setting aside most of all of that work that he had been doing, and instead was excited to learn something new about basic quantum field theory. And to explain why he was interested in learning something new and why this would take over my entire life, let's go back to that statement. So quantum field theory is just modern day force equals mass times acceleration. It's just a set of rules that let you calculate the predictions for experiment. Well, there are two things that every student of quantum field theory knows very well, but maybe you haven't heard, or the first is you can easily appreciate. It's notoriously hard to make these predictions. These predictions require collaborations of giant size supercomputers, decades of efforts often to make a prediction for an experiment like the LHC that's necessary for us to discover something. But this is the part you might not know, which is that every single time anybody's ever made a prediction for any experiment, the actual prediction we make mocks us by its simplicity. And I want to give you a few illustrations of this. But this simplicity, I think, is an indictment on our understanding of basic laws of nature. Because in many ways, you could describe science in general as the mitigation of surprise. And if you are surprised every single time you make a prediction, I don't think you understand it. And so the status of quantum field theory as it's been taught to generations of physicists is that while it's basically correct, better than basically correct, it's the most precisely tested idea in all of science, it does render all but the most trivial predictions, those involving very few particles and at the very lowest orders of approximation, either completely intractable computationally or inscrutable theoretically. And that means we have no idea where these numbers came from. And computational tractability is changing with time. We have supercomputers today that we didn't have 10 years ago. But it's not very rewarding to have just an output of pages and pages of junk. And I want to give you an idea of where this is coming from. And it starts with an old story that I didn't know. I probably might have learned it from Nima, I don't know. But it's an older story and it should have been wider known. I should have heard about it in my quantum field theory class. So it's a shame that quantum field theory is so hard because we need these predictions. And it's not just for collider physics, it's also needed for the approximate theories that people use on Wall Street and for building weapons and for, I'm trying to think of something that's not terrible for the world. It's useful for all sorts of people, just like F equals ma is important for people. Calculus is important for people. But the problem is that even the predictions that we see, so this process here in the picture is two particles colliding and creating four things called jets. This happens millions of times a second at the LHC, now that it's turned on. And the theoretical predictions for these processes were once viewed as completely intractable. And I mean that in a formal and literal sense, in that there was a paper in 1985, I can give you my citation here, outlining the challenges for future colliders, where the authors pointed out that the cross sections for elementary 2 to 4 processes have never been calculated, and their complexity is such that they might not be evaluated for the foreseeable future. They not only acknowledged that nobody had done it, but they thought it was hopeless. And you can see why, especially in the 1980s. Because if you open up a textbook on quantum field theory and ask, what is this prediction? What's the prediction for the standard model of particle physics to have 4 particles come out of a collision? This process involves 220 diagrams And if it involved a week of algebra to do one, this is going to take a while. And moreover, it's thousands of terms and you're supposed to square it at the end. And I didn't tell you about that, but so it turns out to be millions of terms. Okay. And so this was utterly hopeless. You're never going to do it on pen and paper, and you need computers. But it's a good way to motivate people that say that something's impossible. And within a year of this paper coming out, 2 physicists at Fermilab, interested in collider physics, put their backs into it, and they literally threw every computational and theoretical trick at it. They used the world's most powerful supercomputers. They used all this modern ideas in physics, and they really broke their backs and they summed those diagrams. They got the exercise done. And as soon as they got it, they rushed it to publication in this beautiful paper with a 1-sentence abstract. The cross-section, the probability for 2 gluons to 4 gluon scattering, creating 4 gluons, is given in a form suitable for fast numerical calculations. See, they knew their audience. They knew that the experimentalists needed this prediction. Okay, well, what did it look like? This is, by the way, only the leading order, just the first order of approximation. Well, they added it all up and they got it down to a very compact 8 pages. And the paper is basically just this one formula. It doesn't matter that you can't see it. There are a bunch of coefficients, matrices there, and then it's just a bunch of terms, okay? But trust me, it took a lot of work to get it down to 8 pages. But the reason why I absolutely love this paper and why it started a revolution is because at the very end of this paper, they had this quixotic comment that after apologizing for not showing their work, they said, furthermore, we hope to obtain a simple analytic form for the answer, making our result not only an experimentalist's, but also a theorist's delight. I mean, that's a strong phrase. A theorist's delight? What could possibly delight anybody about an 8-page formula? I've spoken to both of these people, the people who did this, Stephen Park and Thomas Taylor, and you know, it's hard for them to clarify it because they just had a hunch. They had a hunch from earlier examples that they thought that this thing would be simple. And sure enough, within 6 months, they stumbled on a guess that must have shaken them to their core. That whole 8-page formula is 1 line in notation that absolutely doesn't matter. And the formula, the meaning of the formula doesn't matter to you either. But the point is that an 8-page formula is equal to that 1 line there. And that's a big simplification that's worth, you know, celebrating over. But what made this a revolution and should have been a beacon for everybody for decades, it should have been more widely celebrated, was that if you stare at this a little bit and you look and you have some intuition about patterns, it inspires a guess for the production of any number of particles whatsoever. And so they guessed that this thing could be generalized to the production of any number of particles, any number of jets. And if this doesn't, to appreciate the degree of simplification that they're suggesting here in this guess, is consider that when 2 gluons create 50, the number of diagrams that you'd have to add up at leading order exceeds the number of atoms in the universe, in the visible universe. And so this claim, this guess, that if you added up all those 10 to the 84, which is billions of billions of billions and billions of diagrams, that everything cancels out and you get 1 term left, is an indictment, I think, on the way these pictures that we draw. Okay, but you know, the history is interesting and complicated, and to be honest, very few people cared about this paper or this result for quite a long time. In part, maybe because it was just a guess and they couldn't prove it. And it turns out it would take about 20 years for anybody to come up with an argument for why this kind of simplicity was there. And that proof came in a trio of researchers at the Institute for Advanced Studies just before I got there. Freddie Cacciazzo, Ruth Brito, and Bo Fang, all of whom I count as great friends nowadays. But this result, the fact that this simplicity could be proven in a different way, that there's a different formalism that when you ask, what's this probability, gives you 1 term and it gives you the right answer, with hindsight, was an incredible gem and a huge hint for something better to understand the basic mechanisms of fundamental physics. And so Nima, who didn't know any of the story, but with a pretty nice cushy position at the Institute for Advanced Study and a lot of influence. When you're, NEMA and you want to learn something, what do? You bring Freddie Cachazo in. So Freddie spent a year at the Institute, and that must have been one of the most productive and exciting years of my life. I was just a young student, and I had to drop everything and just focus and play this game because it was so much fun. We were discovering things left and right. It was amazing. And it was fun to be learning it with my thesis advisor at the same time, from the world's expert, the person who proved it. So we started writing papers, making little discoveries. In fact, we ended up getting so many things that it was hard to communicate with the rest of the world. And it was because we were still stumbling on guesses, and we had these vague ideas, and our papers, we couldn't explain anything to anybody. And so they read like black magic. We had these incredible formulas and then impenetrable discussion about how we got there. And it was impenetrable in part for a justifiable reason, which is that we knew the rules weren't there yet. We knew that we were missing some foundational ideas, and all of our vague intuitions were vague. It wasn't worth explaining it to anybody. But the formulas that we wrote down, these incredible magical formulas, were easily checked. So we were starting to develop this vague intuition that was becoming very powerful, but we still didn't know the rules of the game. And it was a lot of fun to try to do this. And one of the things that we stumbled upon is this paper down here on the bottom right, which is the generalization of that formula to all orders of perturbation theory. It was a very big result. And the night that we got that, we understood how to generalize this. I sat at a cafe in Princeton, and by midnight, I had scooped every single computation every single team trying to make these calculations I had done on my laptop. And everybody else was using supercomputers and spending years. It was a really incredible breakthrough to be able to make these predictions to a much higher degree of precision. So we wrote a lot of papers, as you do, as a physicist. And what this looked like was that we understood now a generalization for this kind of magic, but there were still some missing foundations. So this is the formula they guessed was just the leading order prediction. Well, what does it look like at higher orders? Well, there's some pretty heroic efforts that ultimately would play a huge role in the story. The next correction was known to be pretty simple. But then the correction after that, even using the smart methods, turned out to be pretty difficult. And so the state of the art around 2009 was a wonderful friend of mine, and now actually a postdoc of mine, or an assistant professor of mine in Copenhagen, Christian Vergu, did this heroic calculation at the next order. And he got this very beautiful 12-page formula. Not very beautiful, I don't know. 12-page formula. And by now, I think you can guess what's going to happen next, because we had access to the right answer for the first time, and we could make new guesses and we could check them. And within a few months of this paper, my collaborators and I, using these powerful tools, got this result and these results. And this story was very much like the original guess, in the sense that we had the right answer, we guessed it, we checked it, and it was correct. And what's happened in the last couple of years, really, is that this is now science again. We now understand how to write these kinds of beautiful expressions for every process in the standard model. Well, anyway, these results, at some point in your career, you just staple together all your papers and they give you a diploma. So I stapled together my papers, thesis, and they gave me a diploma. And from that moment on, I was Dr., I guess, Bourjaily, still not professor though. And with a diploma in hand, I moved up to Cambridge, Massachusetts to join the Harvard Society of Fellows. So for those of you who aren't scientists, you might not know that there's this yeoman stage of science where after you get your doctorate, you spend several years doing research, just doing research. It's a nice job to have while you, to see how far you can get. And eventually, maybe you might get a faculty job. It's usually only a couple percent. It's a pretty difficult threshold to cross. Anyway, I was at Harvard, and I'll show you what I did in a moment here, but the highlights was that I was in this really weird club called the Society of Fellows, where my only contractual obligation to Harvard was to attend a fancy dinner every week. And to give you an idea of the kind of dinners and the kind of society that this was, they give every one of their elected fellows a solid silver candlestick. And if you can look very closely there, yeah, they engraved my name on it. So, and I met a lot of very great people, but the society is a very general audience. So I met people who were very smart in linguistics and biology and whatnot. There were relatively few physicists. But by far the most important person for me during my time in Boston was actually not a physicist at all and wasn't at Harvard at all. It was way down the street, quite a long walk away. This guy, who looks like he could be on a surfboard pretty soon, Alexander Posnikov. And it really is, it feels like a discovery in the sense that all of these vague ideas that we were talking about, it turns out the same vague ideas, well, they weren't vague for him, the same words and the same pictures appeared in the mathematics literature. And namely he, Posnikov, had already knew what we were doing and he didn't know that we were doing it. For completely non-physics reasons, he had discovered and really blazed the path using all these ideas. And so together with a couple more, another mathematician, Alexander Goncharov, Nima, Freddie, and my compatriot, fellow graduate student, or former graduate student, Yaroslav, we finally understood those foundations, and it warranted writing a book, laying it all out. And that book was published by Cambridge University Press eventually, and it lays the foundations for many of these new ideas that have been happening. And I appreciate it's probably not the most easy thing to read. But one of the interesting things that you learn when you publish a book that I was not expecting is the degree of the involvement of lawyers. So I was not expecting a 7-page contract from Cambridge University Press, but they sent us one and we all had to sign it. And it itemized every conceivable and inconceivable scenario you could think of, every possible scenario, and even down to what proceeds the authors would get if the book was made into a film. Get 50%. So if anybody is interested in making a movie out of that book, let me know. I think it could be great. There's one technicality that I think I'm going to skip over here, but it really did form the foundation of the rest of my of what I've been doing since then. But there was this problem about the hardest step is actually go from these pictures to the numbers that you want for the experiment. And that step has always been the hardest, in fact. And the first example where anybody could actually go all the way and get to a number at the end, or a function in this case, is this same process of 2 gluons create 4 gluons at 2 loops. And the result, when it was first calculated in 2013, was an 18-page formula in an appendix that, you guessed it, within 6 months collapsed to a single line. And the long-term goal of my research and this whole this ongoing revolution here is to make this manifest, make it obvious that the prediction for experiment is going to be simple, and then exploit that simplicity to extend our predictive reach. And there's a very beautiful cycle here, and once you understand it, you could push it much farther. And in fact, this thing, which required heroic efforts just 7 years ago, was pushed to the state of the art by now my postdocs to 7 orders, from 2 orders to 7, as an indication of how much we can really press these experiments. So I don't have very much time to talk about the last few years of my life, but I want to give you an idea of where I've been since then. I was given this opportunity to become a professor, at least in title, and an opportunity to really build something in Copenhagen. So I just want to give you some pictures here. So Copenhagen, this Niels Bohr Institute used to be Niels Bohr's home. And it's a wonderful institute with a beautiful, rich history and had some amazing people there. That's why I went. The secretary was kind enough to spell my name in a very comical Danish. This is what my office looked like here. And what was my day-to-day like? I was still playing those games, doing those hard calculations, But you also, attend lectures. This is a historic lecture hall here with some really great colleagues. You spend a lot of time together. And I'd go to cafes and scribble notes. That's what my scribbling looked like. And you write papers. Wrote a lot of papers. And you give talks. But something changed in 2017 that really hasn't put me on a very different trajectory that I wasn't planning on. Up until that time, I was really a solo researcher at cafes, sometimes going to the office and talking with people, but mostly, working on my own or with one or two people. But what changed was that there a private foundation in Denmark gave me the funds to really explore some of these big questions. And shortly after that, the European Research Council gave me a very similar grant. And in fact, it turns out there's been a lot of really good funding support for this in Europe. I haven't probed America yet for it, but within just a few months, I went from being all by myself in Copenhagen. My closest collaborator had left, to leading probably the largest group studying this subject in the entire world, with several assistant professors, several postdocs, all of whom, well, I guess everybody in the pictures are still with us except for some of the students. And I'm still see them every day, or every week at least, on Zoom. It's been a lot of fun. But the one thing about Copenhagen that was always true was that it wasn't permanent. And I was on the lookout for a place where I could really grow some roots. And so last year, as Dave mentioned, I moved back to the US. I still have a foot in the door over there, at least while the grants money is still there. Moved to Penn State, which brought back so many great, I mean, I hadn't been to Penn State before I came here, but there's a lot of similarities with Penn State and another city that I love very much, Ann Arbor. And you can see my office, actually, it's just right behind me. This is what it looks like here. And one of the profound things that has really made my life enjoyable was that was one of the most important discoveries of my life, I guess, when I moved here, was meeting this woman, Tasha Smith. Here we can see, we went out very early in the morning. You can see the comet in the background if you look closely. And yeah, I put a ring on it. So this is our wedding from August here. Okay, I want to close on a physics point. Just a couple things about this story and about why it's exciting and why it's rewarding. So the subject that I study is definitely abstract. It's definitely mathematically intense. But there's this virtuous cycle, and it's a lot of fun that you can move from one corner of the cycle to another and find yourself doing very different things from day to day. In many cases, you can start the story with somebody calculating something really hard. You're making some prediction for an experiment that was considered inconceivable just a few years ago. You look for that paper by somebody saying that it'll be impossible, and then you try. And you break your back doing it, you do it, you make the prediction, and sometimes you and sometimes somebody else within a few months invariably discovers that giant formula you calculated is just one line. This happens so often that it's a truism in the field. And then you scratch your head and you think about it. You think about it really hard. Sometimes this can take 5 years or so. And then once you understand why that simplicity is there, you feed it into your technology. You reformulate the basic rules of the game so that that every stage is simple as you go. And once you've done that, you can therefore reach much further. And whether this is for a collider physics experiment, or maybe gravitational waves, early universe cosmology, or just pure mathematical explorations, this has applications to everything. And you can apply these ideas there, and it's just it's been a really fun ride going around this circle again and again. And I think when I'm on the plane and somebody asks me what I do when I say I'm a theoretical physicist, or studying quantum field theory, it usually doesn't get a very good reaction. But if I I think the one way to explain, the simplest way to see what's exciting today about about this very abstract and complicated subject in theoretical physics is that I think it's justifiable to say that we're in the midst of a revolution. And one way to think about this, and I'm sure it's not the only way to think of a revolution. I mean, Kuhn had his own, is when you look around and you find out that every single textbook of an established field is suddenly obsolete. When something has been taught the same way for 70 years and nobody has a textbook that works anymore. It's not that they don't work, but what is true today is that experts who need quantum field theory, whether it's for predictions for the collider physics or for gravitational wave predictions or the stock market, it doesn't make any difference. Nobody is using the tools that we teach our students. And it's a shame. And as a teacher, I'm kind of, I'm very sensitive to the fact that we don't use these textbook tools anymore. But what's exciting about it is that we're not ready yet to write the next generation of the textbooks. They're still being written today. Although we do have a few starts, few things that are pretty well understood. This diagram I drew, I'm kind of proud of it here. But the foundations of the future's textbooks are being written right now. And the people around, my collaborators, my colleagues, we're finding those things. And those things will form the foundations of future generations of textbooks. And this is what's so exciting about this field. So with that, before I wrap things up, I have one more personal comment out there, which is that I'd like to wish my mother and my brother a very happy birthday. I love you both very much. And I hope you've had a wonderful day. And then I'll finish with some pictures of showing you an idea of what it's like to live the life of a theoretical physicist. A lot of good friends, a lot of strange places. So thank you very much. If there's any questions, I understand that there will be some moderation. I don't know how to do that, so.
Yes, we can enable participants to ask a question if they want to mention it in the chat, and then we can allow you to talk.
Yeah, if you have any questions for Jake, you can click on chat at the bottom of your screen and type it in, and we'd be happy to ask Jake your question. That was,
Jake,
that was a great presentation. I really enjoyed it. Yeah.
Jake, I have one just to follow on. So basically, you got your undergraduate degree without going through the standard, you accumulated enough credits to graduate, but you did not follow at all, the typical course, curricula that is laid out, for the 4 or 5 years that students take in that coursework. So how quickly did you finish your undergraduate work then?
Well, I guess it depends how you count. I was a student of physics only formally for 2 years, but I was a student of engineering for a year, so 3 years total. At the university.
And then you said you also had mentioned in an earlier discussion that you had actually taken some of the credits during your high school, during your last year of high school, or no?
Oh, yeah, I did. That's one of what made it possible in many ways. While I was a high school student, my senior year, I was a full-time student at Calvin College. And before that, I was taking night classes at Grand Valley with junior standing, which certainly made this possible.
So there's nothing like being motivated. Forget about the traditional track. Okay.
Well, I don't think we have any questions.
Well, as now I'm on the other side.
Oh.
I was going to say that now that I'm on the other side of the table, I'm teaching quantum mechanics here at Penn State, and I can say that you're looking out for the students who do things that are ill-advised. I want them to be so something that they leave other things aside, that they, make bad choices in pursuit of something that they really love. And those are always the people you want to look out for. Yeah. feel free to pursue your passion at the expense of whatever else you'd like.
Yeah.
Yeah.
Jake, here's a question I asked you last night when we were doing the informal session. Going back to your very first experience, you have a remarkable memory for things. At what age did this passion, this is so obvious, actually begin?
You know, it's really hard to tell. I think my interest in science, I don't know. I mean, I loved rockets as a young kid, and I had a wonderful teacher in middle school for that. I had a lot of very good math teachers, even though I wasn't a good student. So I'm not sure. But I, like most kids who find themselves interested in science, I'm extremely grateful that I was pointed towards the Astronomy Association. It was really, I mean, there isn't anything quite like the first time you look through a telescope and see Jupiter. And there also isn't anything quite like the first time you get to show a visitor at the observatory, when they come off the ladder and have just seen it for the first time. The look on their face is amazing. And so, I mean, I definitely owe a great deal to the practice of science and the sharing of science with my experiences there. I can't remember exactly when. I think I was a member in 1997. Yeah.
I do remember you were a standout right from the start. Very clear.
Well, it's very generous of you, but it's easy to look back with rose-colored glasses, they say.
Thank you.
Well, I want to thank everybody again. I see so many wonderful friends on the list here, and I wish I could be there to shake your hand or to catch up in person. Thank you so much for coming. I really appreciate it, and I hope you learned something tonight. And yeah, thanks again.
Thank you, Jacob.
Thank you, Jacob. Yep.
Thank you.
Pleasure.
All right. Thank you, everyone, for joining us.